Bismillah ar-Rahman ar-Rahim. So we are discussing infrared spectrometry. Previously we discussed the sources of radiations that are used in the IR spectrometry. So today we are discussing the transducers. Okay? So interferometers we already discussed. That is also part of the instrument. So that we previously discussed. So the IR transducers. So we are having three different types of transducers that are used in the IR spectrometry, and that is the pyroelectric transducers, photoconducting transducers, and thermal transducers. Before discussing these transducers, let me know that many of the aspects of these material that are actually related to the material sciences. That is, have deep understanding of the material sciences or the physics and the properties of the material, especially semiconductors. But we are actually not related to those understanding because we are the pharmacists and major emphasis of our syllabus that is on the actually on the pharmaceutical analysis. So we just should know a know-how about these materials, not in detail, but just to have a brief uh, study of these materials, just to understand their functions. So we will be discussing all these three today. The pyroelectric transducers that is found in photometers, many FTIR spectrometers, and dispersive spectrophotometers. Photoconducting transducers are also found in the FTIR instruments, and these are one of the most commonly used transducers in the FTIR. The thermal detectors are found in the older dispersive instruments, but are too slow to be used in the FTIR spectrometers. So it means that most commonly used are the first two, and especially the photoconducting transducers as we are discussing today. So pyroelectric transducers, as the name indicate, pyro is from the heat. So these are some special type of dielectric materials that retain current when they are heated. So they are for that purpose they can be used in the IR transducer. So pyroelectric transducers are constructed from single crystalline wafers of pyroelectric materials which are insulators. That is, they are dielectric materials with very special thermal and electrical properties. Very special, we are discussing that how they are special and they differ from the other such materials. So one of the commonly used material is triglycine sulfate. Triglycine sulfate, and many of the time the hydrogen that is replaced with the deuterium. So that is usually deuterated triglycine sulfate, and often with a fraction of glycine replaced with alanine. So DLA-TGS. And all these are actually to improve the property of the material. So there is most important pyroelectric materials used for the IR detection system. So when an electric field is applied across any dielectric material, polarization takes place, with the magnitude of the polarization being a function of the dielectric constant of the material. So for most dielectrics, this induced polarization rapidly decays to zero when the external field is removed. Now, in case of pyroelectric substances, in contrast, retain a strong temperature-dependent polarization after removal of the field. That is, even when the field is removed, so depending on the temperature, it will retain the current. So thus by sandwiching the pyroelectric crystal between two electrodes, one of which is IR transparent, a temperature dependent capacitor is produced. Changing its temperature by irradiating it with the IR radiation alters the charge distribution across the crystal, which can be detected as a current in an external electrical circuit connecting the two sides of the capacitor. And hope it will be clear. Let me know if there is any ambiguity. The magnitude of this current is proportional to the surface area of the crystal and the rate of change of polarization with temperature. Now, pyroelectric crystals lose their residual polarization when they are heated to a temperature called the Curie point. Curie point is actually the point beyond which these materials that lose current. That is, there will be no current beyond that temperature. When they are reaching that temperature, so they will be having no current. So for triglycine sulfate, the Curie point is 47. So means that they should be operated below 47. When they reach 47 degrees centigrade, so they will not work. Now, pyroelectric transducers exhibit response times that are fast enough to allow them to track the changes in the time domain signal from an interferometer. So for this reason, many FTIR spectrometers for the mid region, IR region use this type of transducers. So hope it is clear simply to uh, cut it short that these pyroelectric materials that retain charge because of the heating when there is change in the temperature, and when IR radiations are lying on these material, so their current that is increased, and this current that is proportional to the radiation or the increase in the temperature. So by this we can know the amount of IR radiation that is coming. The second one, that is the photoconducting transducers. In IR photoconducting transducers, they are consisting of a thin film of a semiconductor material, such as lead sulfide, mercury telluride, and cadmium telluride. That is also known as MCT, mercury cadmium telluride, or indium antimonide. They are deposited on a non-conducting glass surface and sealed in an evacuated envelope to protect the semiconductors from the atmosphere. So absorption of radiation by these materials promote non-conducting valence electrons to a higher energy conducting state, thus decreasing the electrical resistance of the semiconductor. So photoconducting materials, as the name indicates, their conduction or the charge that is increased because of the irradiation by, for example, IR radiation. A lead sulfide photoconductor is the most widely used transducers for the near IR region of the spectrum from 10,000 to 333 per centimeter, that is from 1 to 3 micrometer. That is a near IR region. It can be operated at room temperature. For mid and far IR radiation, MCT photoconductor transducers are used. So as I told you that MCT are the most commonly used transducers in the FTIRs. They must be cooled with liquid nitrogen to minimize the thermal noise. So they are actually working at a very low temperatures. The properties of these transducers depend on the ratio of the mercury telluride to cadmium telluride, which can be varied continuously. The MCT transducer is fast and more sensitive than the DTGS transducers, deuterated triglycine sulfate transducers discussed in the previous section. So it means that they are more sensitive and will be giving more accurate result than the DTGS transducers. So for this reason, the MCT transducers also find widespread use in the FTIR spectrometers, particularly those requiring fast response times, such as spectrometers interface to gas chromatographs and those intended for kinetic measurements. So in these types of studies, these MCT transducers that are more desirable. Then the third one, that is the thermal transducers. Thermal transducers are actually they were used in the dispersive instruments, and they are nowadays seldom used, and they are less accurate as compared to the Pyroelectric are the photoelectric transducers. So the thermal transducers whose responses depend on the heating effect of the radiation are found in older dispersive spectrometers for detection of all but shortest IR wavelengths. With these devices, the radiation is absorbed by a small black body and the resultant temperature rise is measured. The problem of measuring IR radiation by thermal means is compounded by thermal noise from the surrounding. For this reason, the thermal transducers are housed in a vacuum and carefully shielded from the thermal radiation emitted by other nearby objects. Now, there are different types of these thermal transducers. One of them is the thermocouples. So, in its simplest form, a thermocouple consists of a pair of junctions. Junctions are actually interfaces that are used in the semiconductors. You might have discussed, studied in the FEC, P junctions and N junctions. They are formed when two pieces of a metal, such as bismuth, are fused to each end of a dissimilar metal, such as antimony. A potential difference between the two junctions varies with their difference in temperature. The transducer junctions for IR radiation is formed from very fine wires. That is, either very fine wires are used, or alternatively by evaporating the metals onto a non-conducting support. In either case, the junction is usually blackened, that is to improve its heat absorbing capacity, and sealed in an evacuated chamber with a window that is transparent to IR radiation. The response time is typically about 30 milliseconds. And to enhance sensitivity, several thermocouples may be connected in series to produce a thermopile. Then there are bolometers. Bolometers is a type of resistance thermometer that is constructed of strips of metals such as platinum or nickel or from a semiconductor. This type of semiconductor device is sometimes called a thermistor. They are also known as thermistors. The semiconductor material exhibits a relatively large change in resistance as a function of temperature. That is, when the temperature is varied, so the resistance is drastically varied. Now, so this phenomena that is used. So the responsive element in a bolometer is kept small and blackened to absorb the radiant heating. Bolometers are not so extensively used as other IR transducers for the mid-IR region. However, a germanium bolometer operated at 1.5 kelvin is an excellent transducer for radiation in the range of 5 to 400 per centimeter. That is from 2000 to 25 micrometer wavelength. The response time is a few milliseconds. Okay, so this is actually all about the IR instrumentation. The next chapter that will be its applications in the pharmaceutical analysis. So if you are having any question, you can ask the question.
सर ये थर्मल ट्रांसड्यूसर में ब्लैक बॉडी का क्या काम है?
Just